for the introduction. So my name is Srinam Venkatesh. I work at a company called BigBinary, and I also do, I'm active in the open source ecosystem of Kubernetes. So this talk is going to be about how we built our own deployment platform and the story of how we did that. So BigBinary is a Ruby on Rails consulting company, and we have our own internal product suite as well, which is around 25 to 30 apps, like Ruby on Rails and React apps, which are in active development. So till sometime back last year, all the deployments were done in Heroku, and we also had the PR review apps, which are like ephemeral deployments. Whenever a developer creates a pull request in GitHub, we'll deploy that as a review environment, and then when the PR is closed, it will be destroyed. So we had around somewhere north of 100 pull request apps every week, and all of this is done in Heroku. So this is the the Neato product suite that I was talking about. We have like a bunch of different applications for calendar, your appointment booking sort of thing, and you can have different an application to create forms, invoicing and all of that. So Heroku worked for us because it sort of checked all the boxes. We were not a DevOps heavy company until last year, and Heroku worked for us because we could just get the app deployed and not have to worry about it. And this was the case until sometime mid last year, where Heroku announced that they are getting rid of their free plan. So all the PR review apps which I mentioned earlier, they were running on the free plan, and Heroku taking away their free plan would mean that we'd have to pay a very high amount of money for all the around 100 plus PR review apps that we had each week. So we were at a crossroads last year, September, where we had to decide how we have to go forward with our deployments. So we decided to build our own sort of solution. This is not something that we have expertise on or we have done before, but we were willing to take up the challenge. And sometime back in the mid-September of 2022, we decided that we basically decided that we'll do this thing. And this is the sort of architecture diagram that my tech lead drew in his kitchen whiteboard. And we went from the idea, the idea that we are going to build this thing, to actually start hacking on this project within the span of 1 week. And this is the sort of architecture that we started with. I want to tell you how we evolved over the last 1 year, and what all are the different challenges that we faced, and how we solved them, and where we are right now. So before that, I would like to show you a little quick demo of the product as it is today. So I couldn't share my screen, so I had to make do with pictures. So this is really similar to, spiritually similar to what Heroku provides. You can connect your GitHub repository, and with each commit, your app can be deployed. You can enable auto deploy, and you can have different processes for your application. You can scale them. You can have add-ons, which are like databases and so on. And you can define the number of containers that you want to run for each process. You can enable auto scaling based on CPU and memory metrics and so on. You can also view the metrics in the dashboard itself. You have historical and live logs, which you can query through. And also you can deploy any sort of tech stack using cloud native build packs. You also get access to the console of the application, the shell inside the app. And you can also use add alerts and so on. So this is the high-level architecture of our platform as it is today. So I would like to briefly go through all the different components. So the dashboard that we saw earlier, that is the web dashboard part of it, which is written in Ruby on Rails and React. And users can interact with it and connect their GitHub repository and so on. And we have a GitHub app integration which would print all the information to the GitHub, the PR app in GitHub, along with the deployment section in GitHub itself. And on the back end of things, basically when a new commit is being pushed to GitHub, the web dashboard would send a request to a microservice called the Slug compiler, which pulls the image, pulls the code from GitHub and builds the image using something called Kpack. So Kpack is used to build the image within the Kubernetes cluster itself. So we are running all of this on top of an Amazon EKS cluster, and the image is being built on the cluster itself by the Slug compiler. And if your app requires any add-ons like databases or databases like Postgres, Redis, or Elasticsearch or something like that, we provision them as well. Like you get the option to define them in your the config file, and we'll automatically provision them, or else you can provision them on your own. You can define whatever plan you want, like with the based on your memory and CPU requirements and so on. And this will also be provisioned in the cluster. That is being taken care of by another component called the add-on manager, with just whose responsibility is just to provision the add-ons in the cluster. And all of these add-ons, like the red blocks here, are Amazon EBS volumes, and all of these add-ons comes with a persistent volume which stores your data within the cluster. And yeah, we can take backups and all of that, all those sort of things. And once the image is built, once the container image is compiled in the cluster, it is pushed to a self-hosted container registry which is running inside the cluster itself. So I'll go into the design of that in a later slide. But just know that the image is built in the cluster and it's pushed to a container registry within the cluster. And then we have the third component called the Dyno Manager, which actually deploys your app. Like it creates deployments for all the different processes that you have defined for your application, and they'll talk to the database and they'll pull the image from the container registry and so on. So in the end, what you will get is you will get a URL like mytestapp.neatodeployapp.com, and when the user enter it in their browsers, that traffic is handled by a load balancer called Traefik. So Traefik is a cloud native proxy software, which will then route the request properly to whatever deployment that you had created. So this is sort of the high level architecture. We also have a bunch of different components which I'll go into detail in some time. Yeah, so we have been building this for the last 1 year, and some of the challenges that we faced are how do we scale this thing? We want this platform to be fault tolerant, and we want it to work whenever developers want to get, whenever a developer creates a pull request, we want to do all of this thing automatically, and we have to make sure that it works properly, that it is able to handle the load and spike in traffic and so on. So managing scaling was one of the major challenges that we solved. And once we had that done, the next sort of thing that we had was how do we optimize for cost? We want all of this to be available all the time, but we still want to pay only pay only the minimum cost that is required to get something like this up and running. So some of these were solved in these different ways. For the scaling part of the problem, we deployed Cluster Autoscaler, and so Cluster Autoscaler basically provisions nodes and adds them to your cluster. So let's say your Kubernetes cluster is running with 3 nodes. So suddenly on Monday morning you get a lot of traffic, and now your cluster doesn't have enough space to run all the apps. So the Cluster Autoscaler would take care of that, and it would automatically provision a 4th node and add it to your cluster so that everything is there. The cluster has enough space to run the apps, and when the traffic is low, the Cluster Autoscaler would scale it back to the minimum amount of nodes that you have configured. So we did that first, and then we realized that we don't want the users to wait until the node is ready to get their apps deployed. So we did something called the OR provisioning deployment, which is basically deployment of the POS pod. So the POS pod is like the POS container is basically what Docker uses internally to create a placeholder container before the container actually starts. So it's like a empty container which doesn't do anything, but we created an overprovisioning deployment with a negative pod priority in Kubernetes. So what negative pod priority means is that if a new deployment comes, then the one with the negative pod priority will be evicted and the new deployment would be replaced with that. So we created overprovisioning deployments so that some nodes are always running as a buffer, and whenever a developer creates a new pull request or a staging or production app or whatever, the POS pods would be evicted and their deployment can instantly be deployed. That is how we solved the scaling part of the problem. The second part was how we reduced cost. So we were initially running on Elastic Container Registry. We moved that to our own internal self-hosted container registry. I'll talk about that as well. And the last thing we did was turn off inactive apps. So when an app is not being used, we scale it down. Like we scale all the deployments to 0. And the next time the user hits the URL in the browser, we scale the app back up again. So we were able to bring down the cluster usage to a very minimal level during weekends and so on. Yeah, so this is sort of how we evolved over time with how we handled the container images. So initially we were building the image in the cluster and we were pushing it to Amazon ECR, and we had to pay for the egress as well as ingress costs then, as well as the cost for Amazon ECR. Then what we did was we ran our own container registry inside the cluster, and we would build the image within the cluster, push it to the container registry, and then when we were pulling the image, like when a deployment is created, the image URL would be given as the public load balancer URL of the container registry. So the container registry itself was exposed outside the cluster with a similar URL, and you would be able to use the container registry API and so on. And even in this case, we had to pay for the egress cost because the image was being, even though the image was inside the cluster, the network request would have to go outside the cluster and then come back inside again. So how we solved this was using a static cluster IP. So in Kubernetes, like when you create a service, you whenever you create a cluster IP service, there is a range of ports that are fixed for internal usage. So these are called static cluster IPs, and if you create a service with a static cluster IP, that cluster IP would not change. So we use that and fix the IP address for the container registry so that every time when we create the image, we push it to the container registry running inside the cluster, and that network request wouldn't have to go outside the cluster. So we were able to save a lot of money, for network bandwidth this way. And everything stays within the cluster, like pushing the image as well as pulling them when a new deployment is created. And this is how we solved the scaling down of apps issue. So whenever a user requests for an app, all the requests would go through our traffic load balancer. So the reason initially we were running in Nginx ingress, after a while we moved to traffic ingress because they had support for middlewares. So any request that comes through your system, you can define middlewares which will intercept the request, and you can basically do whatever you want with your the network request information. So what we did was, whenever a request comes, if the request is made for a review app, so we only wanted to scale down review apps, PR review apps, and we didn't want to scale down staging or production apps. So we want them to be running at all times. So what we did was, whenever a request comes for a review app, we would intercept the request. We had something called the pod idling service, which would intercept the request, and that timestamp would be stored in a Redis cache. So the pod idling service would have a cron job which runs every 5 minutes, which would go through this entire list in Redis and calculate which all apps were accessed more than 5 minutes before. So if that is the case, then we would scale down the deployment basically. So what this means is your app will be running And if you haven't accessed it for 5 minutes, then it will be scaled down. And this is what we did to bring it back up again. We had like a wildcard ingress route which works as a catch-all sort of ingress route. So even if you type some gibberish, it would go to this downtime service, and it would serve a page called nothing. There's nothing here, right? So from within that service, we checked if that deployment is present in the cluster, and if it's scaled down, and in that case, we would scale it back up and like show it to the user. So for the user, they just enter the URL and they'll have to wait for a couple of seconds until the app comes back up again. So with this strategy, we were able to like run the cluster at the minimum amount of nodes that are required at all times. So the lessons learned, metrics and observability are really important when you're working with the Kubernetes cluster at this scale. And there are a lot of trade-offs. Like there are a lot of knobs that you can turn, and you'll have to find the balance which works for you, which might be different in different cases. And working on hard engineering problems is like really rewarding. Yeah, the future that we have, like we are planning to have a soft launch early next year, and we are still working on like solving a bunch of hard problems. Yeah, I'll be around here. You can hit me up if this is something that you find interesting. Yeah, that's all. Thank you.
Thank you, Sriram. Thank you for a wonderful session. Let me invite Neha to hand over the token of gratitude to Sriram. Can we have a big round of applause for Sriram?
Thank you.
Thank you.